Hi, I'm Rich from PACnet. For those that don't know me, basically here to talk about subsea cable systems in Asia and the impact their availability and repair schedules have on backbone design and planning. So first I just want to do a brief review of subsea operations and repair, also some common outage factors. And the second half of the presentation I just want to go through the design factors that operating in a region that's heavily dependent on submarine cables and what those factors are in your consideration for designing backbones. So first of all, who is PACnet? Just very briefly, we're basically a pan-Asian subsea cable provider and internet service provider, and we wholly own and operate 3 submarine cables in Asia: the EAC system, C2C system, and EAC Pacific. EAC Pacific basically represents 2 independent fiber pair on the 5 fiber pair Unity system. So just as a quick review, high level, subsea cable components typically have your subsea cable itself, which is typically unarmored deep sea cable, lightweight cable, and deep sea applications. And then you'll have additional armoring and protection as you come into shallower waters. You have branching units, which provide stubs or spurs to other markets without having to deploy a completely separate cable. You have repeaters that are responsible for all amplification and equalization needs of the optical signal. And then as the cable system comes into beach landing, typically the cable is buried for added protection, usually anywhere between 1.5 to about 3 meters deep. That comes into a beach manhole access point, which ties into a terrestrial extension to bring you into a cable landing station. Basically, a cable landing station is a hardened facility that has all the optical equipment and the power feed equipment necessary to power the repeaters. So this is just a snapshot of a sample repeater. This one happens to be a Tyco repeater. Basically is a self-contained device that houses all the internal hardware necessary for amplification and equalization of the optical signal. And this is basically what makes subsea operations and subsea cable systems operate over 10,000 kilometer spans. This is just a snapshot of typical repair equipment, deployment equipment. You have a cable ship. It's a specialized ship that houses spare cable. Typically has multiple cable tanks. It's spooled. You can have thousands of kilometers of cable in these tanks. And then additional burial equipment such as plows and ROVs for shallow water burials. This is just a snapshot of a typical subsea cable construction. It does vary by vendor type. Typically start with a unit fiber structure. Basically this is just a polymer tube that houses the optical cable or optical pairs and protects them. Surrounding that, you typically have a high-strength steel wire support that adds support and strength and stiffness to the cable, as well as providing a pressure vessel. Surrounding that, you typically have a seam-welded copper sheath. This pretty much provides a main power conduit for the PFE, which powers the repeaters. And then surrounding that, you have a polyethylene jacket, which acts as an insulator to protect the main power conduit from the natural ground potential of the sea. That's the baseline lightweight cable construction, which is typically used in deep sea applications. As you come into shallower waters for additional protection and adverse seabed conditions, rocky conditions, you have additional armoring and protection. These are just some common fault types. You have a shunt fault, which basically is when the power conduit is exposed to the ground potential of the sea. Fiber pairs remain intact, and the PFE has to reconfigure, rebalance to maintain service, but the segment can remain in service until you can get a ship out to do the repair. You have a cable cut, which is actually a complete cable cut of the segment. Obviously, the segment at that point is taken down. Repeaters, as highly available as they are, reliable and have redundant components in it to protect against laser diode failures. There may be instances where you have a catastrophic outage or event that actually does damage to the repeater, and so then you have to bring the repeater up to either service it or repair it or replace it. This is just a diagram, logical diagram of power feeding in normal condition. So you have power feed equipment at both ends of the cable at the cable stations, one with a positive, negative voltage differential. That supplies a constant current and constant voltage drop across each repeater. And in the center of the system, you have a virtual earth. In a cable cut, or cable fault, the power conduit becomes exposed to the seawater and creates a grounding point. The PFE has to recorrect to maintain a constant current on both ends and maintain a constant voltage drop across each repeater for two main reasons. One is to protect the repeaters from damage, from having too high voltage levels, power levels. And the second is, in a case of a shunt fault, you can actually maintain service on the surviving fiber pair that's unaffected. So in a shunt fault scenario, to be able to isolate and localize a repair to get a ship out to the site to do the repair, you typically take a voltage measurement. So at each ends of the cable station, there'll be a voltage measurement that you can take from the PFE to determine roughly where the shunt fault occurs to bring the ship out to do the repair. In the case of a full fiber cut, you can actually perform additional optical measurement. So you typically do an OTDR measurement, which actually detects basically the backscatter of light on the actual fiber break. That test signal is sent back to the test kit, which is very sensitive equipment and can determine within approximately 30 meters where that fiber fault occurred. And this is, again, over spans that can be several thousands of kilometers. This is a snapshot of the test kit sample test signal. So as you can see to the left, there is a sawtooth diagram that basically shows the test signal amplification as it crosses each repeater. It's approximately spaced every 70 kilometers or so. And as you can tell from the green line in the center, that's actually where the test signal degrades from the actual fiber cut. So at that point, you have to send a repair ship out to the repair. If it's not a complete and clean fiber cut, typically you'll have to do what's called a cutting drive. You actually cut the cable. The cable ship will then head downstream from where the cable cut occurred, typically twice the distance as the depth in which you're doing the cable repair. That's to be able to provide a counterbalance and additional counterweight to be able to pull the cable up to the surface. It'll use a grapnel to hook the cable, bring it up to the surface, buoy it off, head over to the other section of cable that needs to be pulled up, which is the second holding drive. It'll splice in spare cable, typically protected with a joint box, and at that point lay additional spare cable over to the first buoy site. Perform the final splice, and at that point gently lay the cable to the ocean floor. You can't just release the cable, because if you do, it has a significant danger of entanglement and further damage to the cable, and then you have to go back out and repair it again. So this is just a snapshot of that sequence on the timelines that are associated with each repair. As you can see, at a minimum, it takes approximately 10 days, give or take a day, to do a subsea operational repair. But that's a best case scenario. There are additional delay factors that you have to take into account, and that can significantly affect the repair time frames for a segment that your trunks may be on. So the permit application process, depending on the territorial waters that you're in to do the repair, could take anywhere from a couple days, a couple weeks, or even longer. Some environmental factors that come into play, typically weather, additional aftershocks from seismic activity, cable repair ship availability and proximity. So where is the cable ship docked? How far away is it from the actual fault? How long is it going to take for it to head to that fault location? And then shallow water retrieval and burial, additional equipment and time incorporated with actually burying the cable to protect it in shallow waters. So for outage factors, there's two types. There's natural disasters and typically external aggression. So, in summary, seismic activity tends to be the one that gets the most press. Seismic activity in undersea earthquake typically triggers a turbidity current. That turbidity current can actually reach very high rates of speed, depending on the slope of the canyon as well as the density of the material, which basically takes everything out in its path, including undersea cables. Some useful tools that are typically available on the web is from the U.S. Geological Survey. They track seismic activity throughout the globe. And what's interesting is you can actually drill down into specific regions and identify seismic activity areas, clusters, heat maps based upon particular areas that tend to have a lot of seismic activity, and understanding what cables cross those points and what routes may have potential damage to them or have a higher probability of failure. You can drill down into details on the individual earthquake itself, and so I highly recommend you go to the site, root around for yourself, and take a look at the information that's there. Aside from undersea earthquakes, typhoons, as was evident from Typhoon Morakot in August 2009, basically the torrential downpour and resulting storm surge caused a significant amount of debris to wash offshore. and triggered a turbidity current in the Calpine Canyon. This turbidity current actually, the interesting thing about this turbidity current is it actually occurred in two separate flows. So the first flow was triggered during the peak flood, took out two cable systems initially, and then 3 days later a second flow was triggered, and most likely from the buildup of sediment material along the canyon walls. And this resulted in additional cable events. A total of 8 cable systems were recorded to be affected. Some cable systems had multiple faults. And the interesting thing about this is that just because a typhoon rolls in through a particular region, you're monitoring your network and understanding that there might be a potential risk of an outage on a trunk passing through that area, you're not necessarily out of the water, no pun intended, for after the typhoon passes. There actually may be a lag time in terms of susceptibility to outages that may follow from buildup of sediment material on the canyon walls. So the vast majority of outages are actually not environmental. Most are external aggression. Typically shipping and fishing vessels, anchor drops and drags, bottom trolling based fishing where a net will snag a cable and break it. And to some lesser extent, believe it or not, dynamite and explosives based fishing. There are portions of South Asia where this is unfortunately commonly practiced. It's kind of cheating for fishing, but it does do damage to cables. And also piracy. There have been recorded instances of segments or portions of segments stolen for the materials that are in the cable. And most of the individuals stealing the cable, they're not going after the fiber, they're going after the copper. It has a higher intrinsic value for them for resell on the market. So, again, in terms of restoration repair constraints, a lot of things you need to keep in mind, aside from weather, is that there may be other events that are not the norm. And those events may be unique environmental factors, which was evident from the Japan Fukushima plant. There were areas of radiation exposure that made it very, very difficult for cable repair ships and operations to go in and actually do repairs, and had to wait for that to subside before the repair ship could get on site. So a lot of things that you can take into account when looking at your backbone design and diversity is understanding, well, what type of outages will affect the repair timeframes? Is it a shunt fault repair? Does it actually require additional cutting drives? There's additional delays associated with that. Were repeaters damaged from the supplier? Do they have to go out and actually replace and service the repeaters? There's additional time associated with that. As well as the types of conditions and the location of the fault. In shallow water, a lot of times it's diver-assisted repairs, and fast currents and dangerous diver conditions can delay repair time frames. So that may add a few days or even weeks to the repair time frame. So a lot of subsea cable investors, operators, there is a significant amount of research done in terms of planning and risk projection. During the route analysis phase of the desktop study of the design, they do look at cable faults, proximity, probability, seismically active regions, what type of fishing and shipping activity may cause actual further outages. But obviously you can't protect the entire sea. There are certain routes that you have to use just because of geography. One of the interesting things is that a lot of government entities have taken a look at the value that submarine cables are to their local economy. If cable systems are taken out, it has an effect on their bottom line. And so they've taken steps to actually create protection zones where ships are prohibited from fishing and shipping vessels are prohibited from dropping anchor. Now, creating a protection zone is completely separate from actually doing enforcement. So obviously, even if you create a protection zone and you don't enforce it, the issue is that those particular areas are still susceptible to faults. So from a submarine cable operator, some of the things that are at our disposal is we typically can deploy guard boats. Guard boats, given just the vastness of the ocean and tens of thousands of kilometers of subsea cable, they're typically not effective for long-term protection. You can't deploy a guard boat to cover every area that you have submarine cable. Where this is particularly useful is where you have a major event, a portion of the cable system is taken out, and so to protect your restoration capacity, you will strategically deploy guard boats to areas to ensure that no additional faults occur until you complete the repair. So again, for some of these components that go into and impact your decisions on designing backbones, there's a lot of things you need to look at. typically geographical. There are limitations on subsea routes. You can't lay a cable everywhere. There tend to be preferences in terms of laying cable in very deep and shortened paths, just to, again, be more efficient in terms of deployments, minimize the amount of cable that you're actually deploying to meet the need of connecting certain markets. The Luzon Strait is a perfect example of this. Unfortunately, it goes over a major seismic active region, and a lot of cables are grouped there, as we all were aware from the 2006 Boxing Day earthquake. There are also regulatory constraints. You may look at alternative routes for designing diversity into your network, maybe taking through China or some other markets. But you also need to take into account licensing restrictions, ownership rights, termination rights. And so there aren't a lot of options for routes coming in and out of every possible market. You can also do some historical analysis and planning. You can look at particular markets that have a high degree of shipping activity. Singapore is notorious for this. You have a large port backlog, a lot of ships coming into the area. They can't get any access to the port. They're waiting their turn. They'll drop anchor. So in that area, the vast majority of cable faults and outages are typically anchor drops from shipping activity. And again, you can look at other routes in terms of crossing certain shallow seas where there's a lot of fishing activity. So, from a submarine cable operator, we have been looking at ways to make it more efficient in terms of bringing international capacity into a particular market. And some of the things that we looked at is collapsing the cable station and POP. Essentially, moving the capacity, instead of from the cable landing station and terminating to backhaul, shifting it into the metro directly. And one of the ways to do that is look at shifting the SLT to the city center. Basically, in that scenario, the cable landing station remains just as a power feed station. You may have a dry repeater there to extend another 70 kilometers. But some of the limitations are based on distance. So typically coastal cities like Singapore and Hong Kong are appropriate for this model. But other countries in which there's long distances between the cable landing points and the city centers, such as Korea and Japan, this tends to create issues in terms of whether or not this is actually technically feasible. So then the other approach is to go in the opposite direction. And in this instance, you basically build a data center in the cable landing station. And a classic issue is, well, cable landing stations are typically closed environments. So how do you maintain carrier neutrality? How do you have access to diverse systems and routes? It is a problem, but one of the interesting facts is that given the limitations on viable landing points, if you look at international cable systems, most cable landing points are clustered. And so maybe not in the same physical building, but within a few kilometers, you have access to diverse systems. And so it's just organizing an approach to be able to gain access and interconnect to those systems to give the diversity that you need. And again, it's not a one-size-fits-all opportunity. You may look at a hybrid approach where you keep your compute centers and your data centers in the metro environment, but you put a small network node in the cable landing station. And in that case, you can be more efficient in your routing topology. A classic example is US to Japan. So today, a lot of capacity coming from the US to Japan terminates into Tokyo before heading on to other markets. And so one of the efficiencies to look at is put a small network node on the coastal edge in the cable landing station, and you only route traffic into Tokyo for traffic that has to drop into Tokyo. The traffic going on to other markets like Hong Kong and Singapore can route directly off of the ocean front. So from a trunking standpoint, we've seen the migration of fault tolerance go from traditional optical protection, where optical protection was provided by the service provider. The issues with this is lack of control on backup routes and the latency impact that you may have on a backup path, as well as ring interconnects. So interconnects between systems tend to create a common point of interconnect and a single point of failure. So the shift has been into building your own network, doing multiple linear services. This way you have control over the routes that you're taking, as well as the latency performance of each route that you're designing. The issue becomes, what if you get into a catastrophic scenario where multiple systems are taken out? Again, Taiwan was a lesson learned in the sense that even though you may have designed multiple linear paths over multiple cable systems, going through the same pinch point may take out multiple trunks. And then now you're fighting and in a scenario where you're choosing between manual versus automatic restoration, as well as prioritization on being restored with the supplier. So one of the options is that a lot of suppliers are looking at building optical meshes. It's been done in the US. It's now taking a strong foothold in Asia. This is basically setting up an intelligent switching platform using ASON and GMPLS. And in essence, it gives you a lot of control in terms of the routes that are available to you. So you can create a primary, secondary, tertiary routes. You can pick and choose the paths that you want for those backup paths. And you can design it in a way in which the latency performance is within a delta that's acceptable to you. Again, this may not be a one-size-fits-all approach. You may want to look at strategic markets where this makes sense. Hong Kong and Singapore, for example, there are many systems in which latency performance between those markets across separate cable systems is within a few milliseconds difference. And so you may look to actually build your trunks using a provider-supplied optical mesh for protection for one or two of your trunks, but then for routes where the latency differential is significant, you want more control, you can adhere to the linear approach. Say, for example, back to the US, where you may choose AAG or TGN or PC1 or any number of cable systems that are available to you. And so this is basically just an overview of some of the factors when designing backbones in a region that's so heavily reliant on submarine systems, and some of the factors that you have to consider. So if there's any questions, comments.
All right, any questions for Rich?
Hi, Louis Lee, Equinix. Thanks, this is very interesting. I wanted to ask if you guys have looked at, would it be cost effective to have a couple of lookout points on the shore to see, to look at areas where there might be ships dropping anchors, high probability of ships dropping anchors, waiting to come into port, to see if you can detect ships that are not moving any faster than the current?
It's a good point. I think it's the amount of resources that are involved in doing that. Again, depending on how many cable landing stations you have, tracking that activity can be very difficult. Additionally, again, ships tend to take available space where they can when they're waiting for a particular port backlog. And so in that instance, the locations in which they actually drop the anchor change and they vary. And so what may be a particular scenario and high incident location one day may not be the same the next.
Okay, but it could all be automated because you already know where your paths are and you can use your GPS and triangulation to figure out where the ships are. So
that could be a potential solution. It's an interesting one to take back on.
That.
Okay, anybody else?
Kevin Oberman, ESNet. I also find this all absolutely fascinating, even though I really don't have anything personally to do with it at all. As far as the ground return, do you rely on the seawater, the ground that naturally exists around the cable purely, or do you have exposure of the outer metallic protective layer of the cable to the seawater as well?
It's typically the power conduit coming in contact with seawater. It just creates a natural earth ground and a grounding point, and we use that as a reference point for the voltage measurement.
Okay, any others? Going once, going twice. All right, Rich, thanks very much.
Thank you all.